Our next speaker is Engineer Rupert James. He will be speaking on preventative and reliability engineering. Engineer James, he holds a Bachelor of Engineering degree from UTech and is also a certified lead auditor for OSHA 18000 for occupational health and safety management system. He has over 25 years experience in electromechanical system, which has led him to be successful at the Port Authority of Jamaica, where he serves as facility manager. We welcome Engineer Rupert James at this time to make his presentation.
A very good morning to you all. Are you hearing me? Hello, good morning.
Yes, we are.
Yeah.
We are hearing you.
Great. Well, first, let me welcome all the participants, fellow engineers, to the JIE Engineers Week. And the theme, just to restate the theme, reaffirming engineer importance to Jamaica's development. As Engineer Ricketts had said earlier on, I will do a presentation on preventative and maintenance reliability. But I'd change the phase. Just give me 1 second here. I'm having a problem with this technology. Okay, that's almost there. I've changed the name to reflect maintenance and reliability engineering through overall equipment effectiveness. In previous 2 years, we have had presentation on maintenance, and my first presentation focused on the acquisition of assets, whether the asset is a piece of equipment, a combination of equipment for a process line, or an entire plant which has many process lines. And these equipments basically are acquired to create value for the organization. The maintenance arm primary function is to preserve the asset function, to ensure that this asset continue to perform at its optimum performance level, and they ensure the throughput of the organization. On Monday, there were a number of presentations that's focused on productivity and manufacturing. And so therefore, my focus today is to look in the manufacturing side of the business as it relates to maintenance and see how effective the equipment, the process, or the plant is during its manufacturing process. Quickly, maintenance basically is a value-creating process that, when applied correctly, will increase the productivity for the organization. Typically, over my years of experience in doing maintenance, maintenance is seen as a back-building operation, and they're only needed when there's a breakdown. That's an old philosophy that says if it's not broken, don't fix it. If you want to realize the output of the organization, change the philosophy on which you see maintenance. Maintenance is a value-creating unit that, when applied properly, will ensure increased productivity. And maintenance is a set of activities carried out in order to keep a plant or process or equipment, well, I use in service here, but not only in service, but at its optimum performance level. If I take a typical production plant, whether it's a bakery, it's a fish producing mackerel, sardine, or you're producing my favorite brew, beers, the plant has a performance level. With a critical equipment in a bottling plant, it produces around 600 bottles per minute. A typical pump will be producing maybe 200 gallons per minute at 40 or 60 psi. You find that without maintenance, these equipment will fall below these performance targets. Someone will say, well, it is running, but a failure occurs on a piece of equipment when that equipment is performing below its performance standard. Yes, over years, as years go by, the machine gets old. So if its design parameters is 600 units per minute, after maybe 10 or so years, you might have to derate it to about 500 or 550 units per minute. Having said that, let us look at the different type of maintenance before I go into this tool, overall equipment effectiveness. Maintenance umbrella, as you see it, you should strive to achieve less than 20% of breakdown maintenance in your organization. And there are some items in your plant that you can deliberately run to failure, because if they fail, they will not influence the production process. So including those and other stuff, you should try and achieve less than 20% breakdown in your maintenance. On the other side, you have planned maintenance. Try to make your planned maintenance greater than 80% of your overall maintenance. And you see we have preventative maintenance, which speaks to condition-based. Herein, you would look at the machine to see what it is at. There's also some scientific device that you can use to do some measurements, whether it's oil sampling to see the level of degradation in the oil. And based on the level of degradation, you know that a failure will soon be happening. Or you do a vibration analysis on a pump, and based on the level of vibration, you can predict that a failure is going to happen. Once you're able to predict when the failure is going to happen, you can make preparation for the corrective work. Next one is time-based maintenance, where the OEM, or the manufacturer for the equipment, will tell you at a certain interval you need to do these set of activities. Just to say that these are baseline, but as you operate the equipment, you will find more time-based activities that needs to be done. And you can add it to your work, your preventive maintenance plan, and execute them as you go along. Reliability-centered maintenance, the next one on the list. This is a risk assessment that looks at the equipment, the process, or the plant. And the question is asked, you sectionalize the equipment or the plant, and you ask the question, in what way can these equipment fail? What does the failure look like? Having determined that, you are now able to ask the next question, how can I prevent these failures from happening? Once you're able to do that determination, you can now create your maintenance plan maintenance, and have it in your work order system so that at the required time, you can execute your corrective plan. Under the corrective umbrella, you you will, all of this umbrella, all your work orders under the preventative program that you have generated will be executed under this umbrella. But you also have what is known as autonomous maintenance. This is where the operators for the various equipment, whether it's the oven, a filler machine and a bottling line, a packer, a forklift, you encourage the operator to do what is known as basic maintenance on the machine. High-level maintenance, you leave that to the trained technician. And this will give you a better yield in terms of your available time or the uptime of the equipment, because the operator knows when the machine is not functioning at its optimal level. On to the other side, TLC, some people will construe it as tender loving care, but yes, it is tender loving care, because once it is applied, the machine will give you increased availability, and it's tighten, lubricate, and clean. If you keep it clean, keep the machine clean, you're able to inspect. Once you're able to inspect, then you're able to detect if a failure is gonna happen. And having determined that a failure is gonna happen, you are now able to institute a corrective measure. So having given you an overview of what maintenance, the objective of maintenance is, and some of the activities under the maintenance umbrella, I wanted to ask a question: how effective is your maintenance program? Are the equipment, the process line, or the plant producing at its optimal level? So overall equipment effectiveness is basically an international tool that is used to make this sort of assessment. It's a global standard of measurement for equipment process plant effectiveness. It reveals equipment true capacity. It tells you if the equipment, let's say the filling line is supposed to be doing 60 bottles per minute. At the end of the day, you can do assessment, how much have you produced? Is it performing at the level it's supposed to be performing? That says overall equipment effectiveness is a measure to evaluate the productiveness of a machine or process area. Once you're able to apply this tool, you'll find that you have significant benefits to the organization. And there's a terminology that we use in world-class manufacturing known as QCDSM. The Q, quality, cost, delivery, safety, and morale. If you are able to apply the proper maintenance regime, do your OE assessment, you will improve the output of the facility, you'll improve quality, you reduce costs, you will deliver in your products. There won't be any, if it is bun, if it's Bulla, if it is Red Stripe, Heineken, there's been no shortages on the market because you're using all the available time and producing the goods to the quality standard and delivering the goods when the customer needs it. Having achieved those, what you find is that you have a much safer environment because you are now less reactive and more proactive in doing your work, and you find that the employees have a high level of morale. So from the company perspective, the company will understand that OE provides a true view of the capacity that is available. Improving OEE frees up capacity to be utilized more effectively. If you improve OEE, your chances are, instead of doing a 6-day production run, maybe you can do a 5-day production run or a 4-day production, or you can do longer runs for each SKU and saturate the market with your products. From the technician side, it informs the operator of current machine process conditions and enables them to identify major losses, reduce lost time, and maintain a more productive machine. Just looking at this chart here, let me. For a typical production day, a typical production shift, whatever the product is, let us call it widgets, you have available 480 minutes for a shift for production. But for that production, you have some maintenance activity to be done, planned maintenance activity. So you subtract that time from the 480 minutes, which now gives you the available time. But having started to run the machine, you have stuff like changeover, startup issues, ramp up, ramp down, adjustments, and small repairs, small stoppages. That now reduces the time that you have to produce. At the time, the productive time available, you have issues around machine speed because maybe there's a shortage of materials, or in the process line, there's a piece of equipment that is not producing at its optimal level. And so some of the machines has to be retarded, resulting, so you're in lower yield. And so at the end of the day, you have produced at a reduced rate, you have produced X product at a particular time. Of this product, of all these products, if you have produced 10,000 widgets, then you need to ensure that you have produced quality widgets. Now, when the quality people go through and do their check, you might find that you have a 15 or 20% reject. And that impacts your available time because you have to do rework, etc. All right, let us look at the machine losses that we can have in our system. Availability. OEE looks at 3 components: availability, performance, and quality. So looking at availability, look at downtime, which involves breakdown, setup, and adjustment. If you look, oh no, pardon me there. You have the target runtime, you see being highlighted there, and because of the breakdown, these are what you actually achieve. You have minor stoppages or reduced speed. So this is your target speed, and that's what you actually achieve. How well did the machine perform compared to rated speed? And then quality, defects, and rework. Okay. Let's do a typical OEE calculation. Availability, which will be the actual running time, the total time that the machine was able to run. And it's divided by the total time, or the computed time that the machine should have been running. So if the machine ran for a total of 280 minutes, when the budgeted time was 360 minutes, you would have a 0.77 availability. And that is very low. You should strive to achieve an availability in excess of 0.85. Performance. You've produced, your target output is 10 tons, but you have actually produced 6 tons, or okay, 648 pounds is the output, but your target is 1,080 pounds. You have a 60% performance. Quality, having assessed what you have produced, we're now looking at, do they meet the quality standards? And the quality people will do their checks, and so you will have some stuff that are rejected. And so it is good output over actual output, 0.8. The overall equipment effectiveness for this run is 36.9%. That is very low. So there is significant room for improvement in this one. I'm doing now, what you see there is a calculation for 1 week production, because it captures more of the variables, right? For 1 week production, there's a total of 10,080 minutes. But there's thing for maintenance. You might take out a Saturday or a Sunday to do effect maintenance work. And you also, if it's a food producing facility, you need to do cleaning as per quality standard and sanitization to ensure that it is only quality products that goes to the market. So those activity consume time. My calculation there, 1,440 minutes. And so you're reducing the time. 860 minutes become the available time. The run time, now product changes. You have different, let's say a bakery that is producing bread, biscuit, bulla, crackers, different SKU. And throughout the week, you have to produce all of these products. Yeah, it's one line. And so therefore, each time you have to change to a different product or SKU, you have to go through a process of changing and adjusting equipment. These result in time not used for production. And I just did a figure here, 1,589 minutes. There's an error in that figure there. Okay, moving on, I'll have it corrected. The result is that you have a total production of 2.7 million. The target production of 2.7 million, the actual production is 2.17 million. The actual runtime is 5,322 minutes. We're starting from 10,000, and the production stoppages is 1,590 minutes. The performance, having calculated the availability, which is actual runtime divided by the budgeted runtime, we are coming out at 0.77. Looking at the performance, we have actual production divided by target production. Yes, and that is coming out at 0.6. Quality coming out at 0.8, and the overall equipment effectiveness is 36.9. I just want to go back to this slide. It is for a production over a week, because you have stoppages related to product change. You have stoppages related to maintenance, which is a must, and you have cleaning and sanitization. Those consume a number one. But it should not be a decision to increase the available time for production and sacrifice maintenance, cleaning, and sanitization. If you do that, you will end up with poor quality products, far less runtime. Prime causes of production losses. Any production process seldom operates at an optimum speed. There are a myriad of reasons or negative performance impacts that causes losses in productivity and therefore loss of money. These often include process saturation. The machine just can't produce anymore. And one of the reasons for that is it is an age machine. It was rated at new, it's rated at 600 bottles per minute. It can only do 500 bottles per minute. You need to change that performance standard, derate the machine. Equipment failures. Machine breakdown, wear out, are not used properly and are not used properly. If the operators are not properly trained, you will have induced failures. If the technician doing the maintenance on the machine is not properly trained, and you will have what is known as induced failures, and that result in lost time. Okay, we spoke about product changes early on, and while we're running the machine, we have short stops because you have maybe shortage of materials, you have a down the line piece of equipment that has developed a failure, not running at the required speed. And so you have to take it out to do a quick adjustment or a quick change. Let us look at analyzing the 6 big losses, breakdowns. An example, adjustment of equipment to facilitate production process. Machine shut down because of failure. And you see our little fellow on that side. Changeovers, machine stop because materials or setups need to be changed between product/SKU. So that one was for availability. Now we're going to look at performance. Time losses for idling and minor stoppages, as well as speed losses, need to be understood to improve the performance rate. Machine has either no material to process, or it stops for a short period of time, often less than a minute. We also have reduced speed, because reduced speed resulting from downline processes. Okay, so in doing a summary, OEE is I just need to go back here. I said early on that an OEE of 36.96 or 37% is a very low OEE. And so therefore we need to look at what is contributing to this low OEE, do the necessary improvement, whether it is machine availability, poor performance, or quality issues. You can't have a performance of 0.6 in your production process. You should strive to have a performance above 0.85. Also for availability, in terms of quality, you should try to be at least 0.95 for quality. You can't be throwing away 20% of the products that you have produced. So once you have identified the root cause that's giving you this poor performance level, then you can institute a corrective measure to ensure that you maintain the required performance target that you need. So in summary, OEE is a measure of what was produced against what could have been produced. The gap identified all losses for analysis. Calculating OEE by multiplying the availability, performance, quality yields the same value as dividing valuable production time into available time. Identify the discrete losses in the big 6 buckets will lead to improvement ideas to increase OEE. And those are the 6 items you can take away from this presentation. Thank you very much. Any questions?
Thank you very much, Engineer James. All right, we have an item from Kevin Irvine. Now it's a bit wordy. So it says need for and importance of hazard studies done as early as possible on plant-wide systems in support of maintenance plan, an approach in determining appropriate mix of maintenance strategies that is preventative, predictive, reliable centered, and condition-based. In respect of reliability over the life cycle of equipment, there may be different approaches or demands to maintenance, break-in period through to end of life, need to establish targets for condition-based maintenance in terms of equipment probability of failure on demand. So this person is asking you to comment on this.
The voice was a bit poor. See if you can go back through it again for me, please. You get me, Kevin?
All right, let me read this again for you. So it says need for importance of hazard studies done as early as possible on plant-wide systems in support of maintenance plan. An approach in determining appropriate mix of maintenance strategies, that is preventative, predictive, reliability centered, and condition-based. In respect of reliability, over the life cycle of equipment, there may be different approaches or demands to maintenance, break-in period through to end of life, need to establish targets for condition-based maintenance in terms of equipment probability of failure on demand.
That's more than a mouthful, Kevin. Let me, okay, thanks for that question. Once you put a piece of equipment into operation, you need to do a baseline performance for the equipment, and you need to use as a start, use the manufacturer recommendation for the maintenance. As you go along and get more experience with the machine, you can develop other maintenance activities. And the maintenance activities are not restricted to anyone. It can be, if you do an assessment of the machine, you can have run to failure tasks. You can also have condition, so there are some activities that you do condition monitoring. And remember, condition monitoring can also be very expensive. So it depends on the facility. You can also have, you must include the manufacturer time-based activities. And RCM can replace all of those other activities, but you must start out with those and then evolve into RCM. As to what ratio you use, I couldn't tell. Depends on the equipment, depends on the plant.
All right, thank you very much, Engineer James. All right, based on time, we'll ask you to respond or type your answer to the other questions in the platform, the chat. And we'll now turn over to Engineer Ricketts.
Thank you very much.
Thank you again very much, Engineer Rupert James, for a very informative way of assessing the overall efficiency of equipment. A very good KPI. Thank you so much.
Thank you.